Okay, well, we've been doing this assembly language thing in lessons. We're trying to keep from overloading your folks with too much information all at once. I'm using Stevie as the gauge for this. We do not want him to get to even DEFCON 3 levels.
Yeah, we're doing it in bite-sized chunks, pardon the pun.
Yep. Even though the 69 can do words. 16-bit words, that is. Anyways, this lesson, we're going to continue with the command set. We're also going to talk about something that I've been hitting at for a little while, signed numbers. This is where you can do numbers that are negative and positive. And we'll get into that about halfway, about a third of the way into the lesson or so. And it's really not that difficult. It's nothing magical and like that. It's actually using a trick about 8-bit and 16-bit words and like that. So let's go to the next slide. All right. Last lesson, we were basically doing math commands, and we got to continue through with them. And the first one that we're going to continue with is a little unusual. It's the compare instruction. It allows you to kind of test the relationship between two numbers. It basically subtracts one number from the other, but it doesn't save the result. Now you sit there and say, why bother subtracting one number for another if you don't get a result? Well, the idea is you want to see what, as I said, the relationship is about. And the relationship is via the flags on the CPU. Flags are something that gets set or reset based on the operation you do. And then you can test and use that information to carry over into the next instruction. So in the case of the compare instruction, it will set the negative and zero overflow and the carry flags effectively. The half carry is not. But the idea is that you're basically trying to sit there and say, compare one number, which is either in the A or B register, if you're doing 8 bits, or in the D, X, Y, S, and U registers if you're doing 16 bits. Now this will compare against some sort of memory location information. You can do it what we call immediate. That's where you use the pound sign. And that says, like, if you want to see if the number is 3, you would say compare A pound sign 3. And that 3 comes from the actual instruction. But you can also sit there and say, is this in a memory location? Very handy to check things such as an I/O port to see if something is coming through. So it basically allows you to check the status of a number without destroying the number you're comparing against. So it's kind of like a subtract without actually changing the destination location. Sound straightforward?
Yeah, it's kind of, is that similar to like an if then, but faster?
Well, this creates the information for the if then, which we'll be covering in a later lesson.
Okay.
The branch, you have instructions that you can branch based on conditions. In other words, it looks at the different flags like 0 or negative and decides, okay, if it's negative, go ahead and branch. If it's positive, go ahead and branch. And so this sets up for branching, sign or conditional branching that we'll talk about in a later lesson.
Okay.
Right now, we're just going to stay with math stuff for now. All right, let's go to the next slide.
I'm trying. Okay, there we go.
Okay. Well, the test instruction's kind of similar in the sense that it doesn't affect the destination, but it effectively does a load. It loads in the information to set the flags, but doesn't put it anywhere. So once again, the negative and sign flags are set accordingly. The V or overflow flag gets cleared. The rest of them aren't touched, but you can use it with the A and B registers or an 8-bit memory location, such as if you want to check the status of a flag that you got, such as is player dead. You can see if it's 0 or not 0, and they'll tell you whether or not the player has died. It basically just allows you to see if it's negative or if it's 0. And it's another common instruction that we use to set up for doing branch instructions, like branch if not 0 and like that. So
one thing I would mention about a test, because some people might go, why wouldn't you just use compare? Because you can compare with 0, etc. The test is actually a little bit shorter and a little bit faster because it checks less, or basically checks against less things.
Exactly. It essentially just loads in the information to see if it's 0 or negative, where the compare instruction is comparing 2 locations together. And that situation of comparing does take an extra clock. But it's pretty handy. Yeah. So once again, these 2 instructions, while they're kind of math related, are mostly used for doing branches based on the condition flags later. Let's go to the next slide.
Oh, no. There you go.
Okay. Now we have a very specific instruction, ABX. Basically, it's really a special case. It only works with 2 registers. And it was put in the 6809 because they had a similar instruction in some of the earlier 6800 based processors. So they wanted to carry across, and it can get pretty useful too. Basically what it does is takes the contents of the B register and adds it to the X register. And we say, well, why would you only want to do that? Well, if you are calculating how far you want to point your X register to someplace else in memory, this is a pretty handy instruction, especially if you're like trying to figure out how to put sprites on the screens and you're using the X register to point to where it is in memory, and you want to move it to the next scan line or to the next location where the sprites would go. The B register could contain information that you had loaded up from somewhere else to tell the X register to jump. It's also very specific because it doesn't affect any of the condition flags after it adds to it. It doesn't change the contents of the B register. It only changes the X. And it's what's known as an 8-bit unsigned number, which we're going to get into what's going on with that in a moment. But if, let's say, for example, if you got the number 32 sitting in B and you do an ABX, X is now 32 bytes later. Gee, that's the number of bytes that's in a scan line in a Coco 1.2 graphics high res mode.
Mm-hmm.
So it's very handy for that. It's very quick. And the other thing is it doesn't affect the condition code register. So it's just a handy operation, but it's very precise on what it uses.
Yeah, and it's one of the very few instructions on the 6809 that is, as you said, register specific. It's more like the Intel model where you have to use certain registers for certain things. 6809 is really well known for you can generally mix and match whatever you want. This is one of the exceptions.
Yeah, like sometimes there would be a add 8X, add a memory location to X. No, they don't have that. It's just strictly what's in the B register. And I used this quite a bit when I was doing the sprites because my semi-compiled sprites was basically a data stream which contained information that was used to affect the screen, plus information like, oh, gee, I now have to skip so many bytes so I can get down from one scan line to the next. And I'm not only just going down one scan line, I'm moving to the left a little bit. So I might, instead of adding 32, which brings me straight down one, I might have added 31. That brings me down and one to the left. So my sprites are semi-compiled in the sense that the data stream controls how the information is being painted on the screen. So it's a pretty handy command, but it's really weird and unique. It's, as Curtis was saying, the one case where you have to use the specific registers to make it work, which means that when you're designing your code, you have to sit there and say, okay, I'm going to use these registers to do this, and then you have to build the rest of the code not using those registers for something else if you want to be efficient. So anyways, let's go to the next screen, because we're going to talk about signed and unsigned math. There you go. You're on the right screen now. And basically, up until this point, we've been talking about unsigned. This is like an 8-bit number. It's somewhere between 0 and 255, or in other words, between all zeros on the bits to all ones on the bits. The same thing true for 16-bit, whether it be all zeros or all ones, whatever. They're whole numbers, no sign whatsoever. But you could also, with that 8-bit thing, vary the number from negative 128 to positive 127. And a similar thing happens with 16-bit. You can go negative 32,768 to 32,767. What we're effectively doing is using the most significant bit, the highest bit, to refer to the fact of whether or not this number is negative or positive. If it's a 0, it's a positive number. If it's a 1, it's a negative number. And it's just how these numbers flow together. Now, there's no special mode that's going on in the side of the CPU between positive only numbers and signed numbers. It's just the way the programmer is using those numbers. And besides the sign math, operations, things like adding numbers together and like that, offset for the index registers uses signed numbers only. So when you're looking at X pointing someplace in memory, you can have a negative or a positive number referring to it. And this really becomes handy in the case of the stack, as far as negative and positive, because you're always working pretty close to where the stack pointer is pointing. So that's why they went with signed numbers to reference off of the pointers. So you can point to someplace in memory and say, I want 3 steps back, so you do a -3. And you're now referring to a location that's 3 stacks lower on the stack. Same thing with the positive. It all depends on how you're using the stack and how you're pulling the numbers off.
Is that faster than using the decrement?
Yes and no, because if you use the decrement, then you got to do the increment after you're done. So you got to do 2 instructions. Where in the case of indexing like -1, you haven't changed X at all. You just changed the address that some offset and X is pointing to. So it's kind of like a temporary location.
Gotcha.
So it does make it faster. And trust me, indexing, when we get into that, is the real killer app for the CPU, because you're going to index out the wazoo. So your pointer is going to point to someplace, but you've got information that you want to access. It's off that pointer. It might be 3 bytes in is the current X position of your particular object on the screen. And it just allows you to do object-oriented coding so nicely, which is what all the hip boys and girls do when it comes to coding.
The hipsters.
Yeah.
Right.
Because once you get an object running, you can create the same thing running on the screen in a different place by creating another object. And you don't have to keep reinventing the wheel. You got all these objects running out there. Anyways, let's go on. We're going to talk a little bit about how the math works on the next slide. Okay. This is how the relationship is between unsigned and signed numbers when we're talking about 8 bits. Now in the middle, you see 0, 0. Hey, that makes sense. 1 is 1, 2 is 2, and etc. going up to 127 is 127. But if we look at the top of the screen, let's see, 128 is actually -128. And 129 is negative 127. The numbers start in the signed area. They start at the larger number and they work their way down to 0, where in the case of the unsigned, referencing back and forth, it's the exact opposite. Counterintuitive, but it's because we're dealing with negative numbers.
Let me see if I can follow this right now. So we're looking at 8 bits. The high order bit is 128. When we're doing a sign, that high order bit is really a plus or minus toggle. And so 128 being on has toggled what, the minus?
It has done the minus.
So just by being on, it's basically said that I am minus and I am minus myself because I happen to be bit 8.
Mm-hmm. Okay. But it also has to do what happens when you add these numbers together, which we're going to get into a moment. And just remember this one here, 255, which is all the bits being turned on, is actually -1. When you turn all the bits off, it becomes 0. Let's go to the next slide. Now we're looking at a 16-bit number, which is the other type of signed unsigned numbers that the CPU use. And it's kind of similar. Now, the 32,768, that means the most significant bit is set, all the other bits are 0, kind of like what we saw with the 8-bit. And they work through the same thing. Now, we're going to come back to this slide. Let's go to the next one because it'll really explain what's happening. All right, we're going to talk about 8-bit. Now, in the first slide that had our 8-bit numbers, -1 was 255. And as you can see, that's all the ones together. The percent sign means this is binary. So that's why I use this reference. And we're going to add -1 to 3, which is all the bits 0 except for the bottom 2. In binary, 1 is 3. Someday I will get you guys to not even need to think about it. You automatically will know that.
Oh, yeah.
Yeah, right. That's when you go to DEFCON 1 there, Stevie.
Yeah, no, I've taught binary for years. I understand 8-bit binary.
Yeah.
So
anyways, the answer, if we add these two numbers together, 255 plus 3 is 258, which the answer is a 9-bit number. Wait a second, we only have 8 bits. But let's see what it looks like with the 9-bit. We've got the most significant bit set of the 9 bits, and we got the 10 at the end. As I said, if it was 9 bits, but we don't have 9 bits. We only have 8. That 9th bit just kind of disappears. It goes off the ether, and like that. It'll set some of the flags, but we'll talk about that later. Anyways, the answer as 8 bits is 000010 or 2. So you can see we added -1, but because we are limited to 8 bits, we lose that 1 bit and the number becomes what we're actually doing, which is 2. So a -1 added to 3 becomes 2. See how the sign numbers work? There's nothing special we're doing to the CPU. We're not, other than the fact that because we're limited in number of bits, we lose a bit. It doesn't matter to our answer, and we get 2. So we added -1 to 3, and we got 2. And that's how that works inside the CPU. So,
and this is known as 2's complement math, right?
Right. So it's not really that difficult. And most of the time when you're working in the assembler, let's say that you want to sit there and say, add -2 to the A register, you can actually put down -2. The assembler will put it down. Excuse me, if you want to add -1, the assembler will put it down as 1 1 1 1 1, all ones across the way, as what it represents as -1. Add it to the 3, and then you get the answer of 2. So there, as I say, there's nothing special we're doing as far as setting the CPU into, hey, we're doing signed numbers opposed to unsigned. It's just the way binary works. And this is why we use binary in the CPU. It actually makes math easier. And of course, since they want to do it fast, it works out great. This is another reason why in assembly language, when we're using these integer numbers that are signed or unsigned or whatever, they're so much faster than what BASIC does, because BASIC uses as decimal, based on decimal. And it's got exponents, it's got the whole 9 yards, and it's an awful lot of work and calculations, where this thing here can be done in one instruction. That's what makes assembly language so much faster. You're stripping away the stuff you don't need. Now, Curtis, in the case of BASIC 09, they have integer variables, don't they?
Yes.
And that makes the integer variables so much faster than the full real numbers that are part of the decimal with exponents and all that kind of stuff.
Yeah, I put up a video demo a while ago of BASIC 09 versus disk extended BASIC, just poking the text screen, 512 bytes, the 32 column screen. Mm-hmm. And it's literally probably about 10 to 20 times faster.
Yeah.
If not more.
Yep. It's just the microprocessor internally can do this. Now, later, more advanced processors, they put in math coprocessors that can do all this stuff in base 10 with exponents, and they have built-in functions to do all the mathematical stuff too. Things like trigonomic functions and square roots and all that kind of stuff. But we don't have anything like that on our little 6809. It was a fairly simple chip. In the early days, none of the CPUs had math coprocessors. Even the big, huge mainframes didn't have them. It was much later they started adding them in. Hey, Rick, there was no math coprocessor on that PDP-11, was there?
There was on some models, but not the ones that I ever dealt with.
Yeah, the ones that you
extra.
Yeah, they were extra, like $100,000 or something like that.
Probably.
Yeah, they were quite expensive.
Yeah, we didn't have one in our PDP-1134. I know that.
Yeah, so it's just that this really simple.
The fancy ones would have like a Q register, which would have the quotient for a divide operation.
Yeah. Sometimes some processors had multiply and divide put in, but it was rare to see that.
Right.
And actually, in our next lesson, there'll be a math function I'm going to throw in that I didn't talk about in this lesson, which is multiply. And that multiply command is one of the reasons why Vectrex used the 6809 for its vector display. Made it very simple. In any case, let's go to the next slide. And very quickly, we're going to be talking about doing 16-bit signed math. So because writing down 16 ones is a lot of digits to put down, I decided to write this down in hexadecimal. They're the same numbers, whether they're binary, hexadecimal. It's just that it makes it easier to write and read. Anyways, -1 in a 16-bit signed number is 65,537, or FFFF, or all ones. Kind of like what we did with the 8-bit there, but with 16. And we're going to add to 3, same sort of number there. And if we come up with the answer, we add those together of 65,540 if we had 17 bits, but we don't. We only have 16 bits. So we lose that top bit. And so our answer is 0002, or in other words, just simply the numeral 2. And it's that because we don't have 17 bits, the way this math works out, we get the signed math works. As I said, no special mode you're putting the CPU in, and like that. Okay.
So it's basically chopping off the leftmost bit, and then you're getting a positive or negative value based on if that bit is on or off.
Exactly. And it works out great. It really does. And once again, it's very fast. Okay, let's go to the next slide.
Okay. There we go.
All right, we're going to talk about sex here.
Grant Leedy.
Always wondered about why they put this command down this way. But sex stands for signed extended. Sometimes you've got a signed 8-bit number, but you want to expand it out so it's a 16-bit signed number. And there's all sorts of compares you can do and branches you can do, but they put this one command in where in the B register contains your 8-bit signed number. And then what it does is it extends that sign all the way into the A register. So basically, if it is a positive number, the A register becomes 0. If it's a negative number, it becomes 11111. In other words, 255 all the way across. All the bits are set. And that's effectively what it's doing there. But what it does for the final answer is it's a 16-bit version of your 8-bit signed number. So it can vary from a negative 128 to a positive 127, but the B register now reflects the complete sign that it needs to be. It does affect the negative and 0 flags, and the V flag is cleared. The rest of them aren't affected. But the idea is that sometimes you have to convert 8 bits to 16 bits, and they gave you a command that does all the work for you in one instruction. Otherwise, you'd be doing a bunch of branches and loads, and we don't want to do that. So it's a very fast way to convert an 8-bit sign number into a 16-bit sign number. But the 8-bit sign number must be in the B register, and the A register will continue across. So now your D register has the 16-bit sign number that was just in the B. Pretty much straightforward, right?
Yep.
Yeah. Okay, let's go to the next command. Negative. Well, I didn't include this in the last lesson because I needed to go over signed numbers in the first place. And this is a command that works with it. Now you can, negative basically takes 0 and subtracts the source from it and then puts it into the, that becomes the destination register. So basically, if you said negative A, it basically takes A and subtracts it from 0 and puts it into A. B does the same thing. It subtracts B from 0 and puts it into A. And the reason why we make these special negative commands, we do an awful lot of negativing in our code. Like, for example, I might be working with some math numbers and the answer did come up negative, but I would prefer the answer to be positive. So I'm, like I'm checking the distance between 2 locations and I subtract A from B and I come up with a negative number. Well, if I do neg, that inverts or negative the number, and I now have the positive distance between those 2 objects. So it's a real fast way of flipping the sign on the particular number. And not only can you do a negative on the A and B registers, but you can also do it on an 8-bit memory location too. So if you have a flag that you're a variable that you're using, you can negative the number. And it affects the negative, the carry, the overflow, and the 0 flags. The half carry is not affected. But it's a very useful command for dealing with positive and negative. Pretty straightforward.
Yeah, I think so. It's not inverting the bits though, right? It's not just not
inverting
binary.
the bits.
Okay.
No.
It's inverting the signed number, so a positive becomes a negative and a negative.
So it's just changing the high order bit, basically.
No, it's doing a complete conversion. So if you've got -1 and you hit it with the negative, it'll become +1, which is a lot more than just changing the higher bit. It'll go from all the bits being set to only the 1's bit being set. It's effectively subtracting from 0.
Okay.
Yeah, it's doing a true negative.
And this is a hardware operation that doesn't require a software process?
Yep, it's built into the instruction. Later, we'll get into an instruction called complement, which actually inverts all the bits, but that's in our next lesson where we talk about bit manipulation. All right,
Okay.
let's go on. Now that actually brings us to the end of today's lesson, because we're going to get into bit manipulation and shifting and things like that, because back in the early days of processors, we did a lot of bit fiddling. If you want to change something graphically on the screen, you had to fiddle the bits of the screen to get what you want up there. And so we're going to get into ANDing and ORing and complements and stuff like that in our next lesson. So let's see, what are the questions now? I wasn't looking at our chat.
We had a couple of comments. One of them from Paul Fiscarelli. You had shown a number that was greater than 64K. I think you had shown it as 65537 or something like that. And he says it should have been 35, which for those of us who understand that, we get it. That was probably a typo.
Yeah, it could have been.
Yeah. And then 60, our good friend Karen Anscombe was saying, in 2's complement, neg effectively becomes invert all bits and then add 1.
Right.
Okay. Cool stuff.
Yeah.
And so Grant, you took me off of full screen. Good job there. I would say if we're going to have if we want to have a little bit more of a technical talk about this, maybe we should take a quick break before we do, but I think I followed a lot of it and, I liked it.
Mm-hmm.
How about you guys? Some of this is not new to you. Okay.
I got lost at sex.
Well, you lost your sex when you had your operation, didn't you?
Didn't we all?
Hey, I have to admit, I was like kind of in my teens or very, very young college years when I ran into the sex command. And of course, like any kid that age, I was just having a great time. Oh, sex command. This processor's sexy.
I remember, I think it was the original Byte article describing the 6809 in 1979 or something like that, where they said they had the chutzpah to put the sex command in the instruction set.
Yep.
Yeah, and it's a Yiddish word. It's actually pronounced chutzpah.
Oh, is it?
So, yeah. So
I Canadianized it for you.
Yeah. So, yeah, Rob Inman says sex and bit fiddling. So whenever you can't have real sex, you might just fiddle your bit.
Oh, Jesus.
Well, after our break, I do have a couple of things to talk about in our tech segment that follows up on this.
All right. How about we take a break, Grant, and then we'll come back with some more follow-up discussions.
All right.
Hey, fiddle your bits if you have to.
All right. We'll be right back after these messages.
This concludes another episode of Coco Talk, the world's leading live talk show featuring the Tandy Color Computer. For all things Coco Talk, visit us on the web at cocotalk.live. We'd love to hear from you. Send feedback, suggestions, even segments via email to cocotalk@cocotalk.live.
Cocoa Talk is rocking the 8-bit world, keeping the tandy flame alive. We may be mocked, but we'll never stop, 'cause Cocoa Talk is rocking the 8-bit world.
Consider supporting the show with a purchase of merchandise from our retro swag shop at 8bit256.com. If you'd like to become a patron of the show, click the Patreon link at our website at cocotalk.live.
Cocoa Talk is rocking the 8-bit world, keeping the tandy flame alive. We may be mocked, but we'll never stop, 'cause Cocoa Talk is rocking the 8-bit world.
Cocoa Talk would not exist without the community, its cast, crew, and contributors. Thanks go to Curtis Boyle, David Ladd, Mark Overholzer, Grant Leedy, Bruce Moore, Nick Marentes, Ron Delvaux, Rick Adams, Jason Reichert, Richard Lorbieski, Jim Brain, Tom C., Rob Inman, Mark Bosley, Brian Joyce, Ken Reichert, David O'Connor, Brian Weasler, Terry Steggy, Nick Marotta, John Strong, and many more, especially to Steve Bjork for production suggestions and James Differendaffer for making my head explode. Please help support the Cocoa community by visiting some of its various contributors. A list of resources is available at imacoconut.com. That's imacoconut.com. The Cocoa Talk theme song is copyright 2008 by D. Bruce Moore and Greg Sheeler. Mixed, mastered, and produced by D. Bruce Moore.